Okay, I'm going to keep this short. It's a nice and important topic, so I'm going to report it as usual brief, but this is even briefer. This is a figure from this paper which talks about the density of krill distribution. If you don't know what krill is, you should look it up. It's like a shrimp, and it highly abundant in the Southern Ocean, around Antarctica, and it's famous. Krill is famous basically because they occur in massive blooms during the southern hemisphere spring, and whales all the way from the northern polar regions come across the equator down into the Southern Ocean to feed their calves, because krill is a very nutritious meal for them. And with global warming, there are many details. Krill swim at an angle. They are not horizontal because apparently they are not neutrally buoyant. So if they stop swimming, they sink. So they are always swimming. But the other theory is that they swim and make the waters so turbulent that the predators cannot see them. So there are penguins and others swimming around, but when a big whale comes, it's going to open its mouth and take gallons, maybe thousands of gallons of water. So that's not going to care about turbulence. But nonetheless, with Southern Ocean warming, the uniqueness of the Southern Ocean comes into picture because it's a channel much more wind energy can go into it compared to the other oceans, because other oceans have boundaries, which means warming can also go pretty deep and go into the Indian Ocean, Pacific Ocean, Atlantic Ocean, and so on. And the winds have shifted. The subpolar polar front have shifted here. So the data on krill is not enough to say whether krill are shifting in latitude or they are changing in abundance, and there is even a theory that predation on them has decreased, so they are growing too many in numbers and there is not enough food, so they are dying from starvation. So it's a complicated story, but this main paper I'm going to read basically says Antarctic Krill Sequester similar amounts of carbon to key coastal blue carbon habitats. So that gives you a sense of just how important they are in the global carbon cycle. And of course, Southern Ocean is very important in the global climate variability and trend as well. Okay, the carbon sequestration potential of open ocean pelagic ecosystems is vastly underreported compared to coastal vegetation blue carbon systems. Here we show that just a single pelagic harvested species, Antarctic krill, sequesters a similar amount of carbon through its sinking fecal pellets as marshes, mangroves, and seagrasses. So blue carbon is considered a rich target for, let's say, ocean drawdown of carbon dioxide, what we call ocean CDR, and aquatic vegetation like mangroves and seagrasses, they don't burn down, they are in the water, and they sequester 3 to 10 times more carbon than land forests according to some estimates. So that means krill is also a substantial contributor to carbon sequestration. Due to their massive population, biomass, fast sinking fecal pellets, and the modest depths that pellets need to reach to achieve sequestration, which is a mean depth of 381 meters, Antarctic krill fecal pellets sequester 20 million tons of carbon per productive season, so that is spring to early autumn. This equates to US dollars 4 to 46 billion, depending on the price of carbon, with krill pellet carbon stored for at least 100 years, and with some reaching as far as the North Pacific, so it's carried with the global thermohaline circulation. Antarctic krill are being impacted by rapid polar climate change and an expanding fishery. Thus, krill populations and their habitat warrant protection to preserve this valuable carbon sink. There are also nice stories I have recorded elsewhere how whales may be doing iron fertilization. So whales eat a lot of these krill, concentrate micronutrients like iron, and they poop it out, which can act as a natural iron fertilization to enhance photosynthesis and carbon capture. And remember that Southern Ocean is a iron poor region, a high nitrogen, high nitrate, low chlorophyll region, because all that nitrate is unutilized because iron, the critical micronutrient, is not available in large quantities and so on. Okay, so just to jump ahead, they do a lot of calculations, they validate, and they are providing lots of details on the methodology and so on that you can read. I'm going to skip all that. So here is global coastal vegetation blue carbon stores, so tidal marsh, mangroves and seagrasses, and you can see the numbers in terms of the area, millions of this is the open ocean sequestration in the middle, but million kilometer squared area, tons of carbon per kilometer squared per year, and million tons of carbon per year total. So tidal marsh 13, mangroves 24, and seagrass 44. So a lot of people are pushing for protecting these, growing these, recovering these, and so on for the blue carbon, because blue carbon has a lot of other advantages of improving habitats, increasing oxygens, fisheries yields, all those good things. Circumpolar Antarctic krill blue carbon stores here, feces, that's the fecal pellets, area 16 million square kilometers, tons of carbon per kilometer squared per year 1.3, and million tons of carbon per year is at 20. And then there are other ways of the things that happen. Molds sequester another 20, but migration of daily and seasonal. So you have seasonal migrations and daily migrations, which can be vertical as well. So let's read what it says. Comparison of krill pellet blue carbon with coastal vegetation blue carbon source. The krill pellet carbon sequestered in million tons of carbon per October-April growing season is given and converted to per square kilometer. The krill sequester less per surface area of the ocean than coastal vegetation on vegetation blue carbon, but the vast area krill habitat puts but the vast area krill inhabit puts the pellet carbon sequestered in the same order of magnitude as the coastal vegetation stores, according to data by some Bertram et al. We also include, so you can compare the areas here. They are fractions of 1, whereas here it's at 16. We also include best estimates of the contribution of sinking molds and daily migration, so active transfer of CO2. If these are correct, krill could sequester a similar amount of carbon as seagrasses do globally. There is insufficient data yet to do this analysis for krill carcasses, but we include them graphically, as they are an important carbon sink as well. Note that the other krill habitat size estimates find krill habitat to be 19 million kilometer square using a different grid resolution. So there are uncertainties which they provide as well. Conservation perspectives then. I have a nasty cold. The krill-dominated habitats of the Southern Ocean are akin to better documented salt marsh, mangroves, and seagrass habitats. Not only do they support unique, valuable, and iconic species, but they are also key conduits for carbon storage. Both of these facets warrant the utmost importance of conserving krill into the future. The value for krill is in the order of billions of dollars in terms of carbon storage that benefits society as an ecosystem service. Well, we're talking about social cost of carbon, which is always tricky, but you don't need any real cost-benefit analysis to understand value, right? Krill are under threat from warming, resulting in loss of habitat, potential changes to food availability and competition, and from the krill fishery itself. Whilst there are some fishery restrictions and protected areas in place in the Southern Ocean, more needs to be done to ensure this carbon sink can remain active into the future. It's not clear how a different upper ocean community with less krill may look and the implications this has for carbon sequestration. Though other low trophic level pelagic organisms are increasing in number in the Southern Ocean, such as salps, their efficiency in transferring carbon deep enough for sequestration is not always as high as krill. So this is a bit of a tunnel vision on carbon and krill, but if you think about the whales and other ecosystem services, then of course the krill versus salp has to be considered more carefully, or krill being replaced by other lower trophic pelagic organisms has to be looked at. And this is also a good example of how the biology always finds the loops within nature's rules. So nature is doing something, human beings are doing something, Southern Ocean is getting impacted, krill are suffering, but other species will fill in the niche as far as possible, right? So you can focus on carbon sequestration of replacing krill with salp, but you also have to worry about what it means for the entire food chain in the Southern Ocean. Okay. For instance, salp pellets do not always penetrate into the deeper ocean in such high numbers due to their fragility, which means they disintegrate, compared to dense krill fecal pellets. These subtleties illustrate the complexity of the biological carbon pump. You know the solubility pump, carbon biological pump, you can look it up elsewhere on my channel. Antarctic krill are clearly important vectors of carbon sequestration. The large uncertainty in our understanding of future pelagic communities and carbon export under climate change means we cannot predict with certainty how future change in the krill population will affect the magnitude of carbon sequestration in the Southern Ocean. Our study highlights the importance of Antarctic krill and likely other components of the biological pump in sequestering carbon, which is on par with coastal blue carbon stores. Okay. Sorry. This study and others are increasingly showing the importance of krill and other zooplankton in structuring Southern Ocean food webs and cultivating a strong biological pump. Understanding the relative roles of the key phytozooplankton and micronecton functional groups in the carbon sequestration is therefore an urgent priority. Valuing pelagic vulnerable marine ecosystems in terms of carbon sequestration, like that of Antarctic krill, emphasizes how crucial it is to meet climate goals and work towards including carbon policies in resource management. Okay, that is the entire idea of the integrity of the ecosystem and how that's being affected by human imposed changes in the Southern Ocean, and how carbon sequestration by those species is going to be affected as well. Okay, so I'll leave it here. It's short, but I think it's important. So let's move on and see what the next topic is. Okay, see you in the next podcast.